Good morning, and thank you for having me speak to you today. It's my project, and I'm looking at an improved proximal sensing capabilities in low background oil contamination detection in soils. Just a little about me. My training is, I'm a geologist by training. I did a bit of work in the field as a field geologist for an exploration and mining company. Then my interest switched to oil, and then I studied a master's in petroleum geology in Nigeria, then came to the UK to study environmental geoscience, another master's, and then PhD, focusing on oil contamination detection and monitoring. I do a bit of part-time teaching at the University of Portsmouth. I did some part-time research work as well. Looking at the dust to source project for the wind farm facilities. Graduated in June and in the job market. So if you have a vacancy for me. Yeah, so just a brief outline here. We're going to look at the rationale for the study, the objectives, the experiments I conducted, the research outputs and the possible applications, and then the conclusion. So as you can see, most of the earlier speakers have spoken so much about marine contamination, and there's very little that has been spoken about in terms of oil contamination in the terrestrial environment, especially in bare soils. And we know that for the very reason that tons and tons of our foods are being produced in the soil, it is absolutely necessary for us to consider the oil contamination in the soil as well. These speakers, these scholars, Sterling and Buchanan 2008, actually estimated that the area covered by bare soil is about 35 million square kilometers. That is about 26% of the total landmass covered by the terrestrial environment. And we also know that these bare soils, or the land in general, are either exploration sites, especially for the onshore exploration. They are sites of production. Refineries have been sited there. And then, of course, there are kilometers of pipelines that have traversed through the soil. And they are all potential sites for oil contamination. And if you consider the arid regions, you will know the scale of what I am talking about. So one significant thing is to actually look at what are the acceptable limits for having total petroleum hydrocarbons or oil spill in the soil. So in most of the places, especially in developed countries like the US and the UK, for any spill to be cleaned up, the permissible limit is about 100 milligrams per kilogram. That is about 0.1% of total petroleum hydrocarbons. And then most of the techniques that are being used in the industry today, or even in research institutes, do not actually meet these capabilities to be able to measure these low concentrations. Especially the resistivity, the GPR, all of these do not provide the answers. And even the GC, which is one of the most efficient techniques for measuring oil concentration in the soil, is quite costly and sometimes time consuming for you to be able to carry out analysis of that. So my research actually considered the visible near infrared spectroscopy as an alternative technique to see how we can be able to meet some of the low background testing. So my research actually considers cost-effective technique, which is more like the near infrared spectroscopy, and to be able to measure low oil concentration. Although other objectives include the enhanced detection, to be able to see how much we're able to measure, up to 40%, and then to consider this technique, whether we're able to do in situ monitoring, and then to also consider soil-oil interaction or the sorption capacity, whether we're able to measure the sorption capacity of the soil in terms of soil-oil interaction. Because there are techniques such as the thermal desorption technique, which has been used in many countries or many industries today to clean up the oil. So my experiments that I conducted, I got some soil, artificial soil samples, as well as the natural soil samples within the UK. And then I dose them at different oil volumes from 0%, that is the clean one, and then 0.25 added up to 4 mils of the oil, to get a range of concentrations from 0 to 40%. And then I use an ASD Lab Spec 4 spectrometer to measure the oil concentration. And so this is what you're going to get. The traces you see here, these are the spectra that you're going to get. So it's important for us to actually characterize the uncontaminated samples from the contaminated samples. So one of the ways to do that is actually to identify the soil absorption peaks or the soil signatures. The significant minerals are the clay minerals in terms of absorption anyway, and then there are other carbonates as well, which are also significant. So I concentrated on looking at the clay and then the carbonate signatures. And then when I added the oil to the soil, what I actually discovered that there are additional signatures which are resulted from the oil contaminants. And I actually looked at 1 to 10 nanometers, as you can see the red ones here, 1725, 23, 10, 1720, 1764. So these oil signatures are quite significant. One of the most useful oil signature that has been used in the literature is 1725, which has been used in tons and tons of literatures to build PLSR models for estimating the concentration of oil or for predicting oil concentrations in the soil. But reports have shown that these are not exceptionally efficient. And so I tried to take some of the samples, for example, the wheat rain formation samples, and then the wilt clay formation samples, and some of the Lewis nodular choke. And then I looked at what is the predicting capability of using just the 1725 nanometer signature. And as you can see from the coefficient of determination, some of them look quite good, but not so good in terms of estimating the oil concentration at 0 to 5%. As you can see, most of them are 0.4, 0.8, and 0.48. The only significant one, which is quite good, is the FSS11 there, which is a Lewis nodular choke sample. And by choke sample, having just a single mineral, or carbonate mineral, you can imagine, yes, maybe that's why it's quite exceptional. So I used the signatures in a number of algorithms, and then I came up with this particular simple formula, which I wasn't supposed to show, but I've decided to show it today. To see if we can have an improved detection of the oil at low concentration. And this is what it shows. So the top ones is the same ones I showed earlier, where you can see the coefficient of determination, or the R square, are quite low. But when I use the TPH index, you can see how the coefficient of determination has greatly improved in just a simple regression technique, where you have from 86 to 99, 48 to 98, and then 46 to 97. And of course, looking at the bigger scale, just like I said, I'm not only concentrating on the 0 to 5%, but also the capability of this particular index to measure the oil concentration up to 40%. But one of the things that I discovered, it is possible that you can have different soil samples to have a different response. And this is what I try to do. I classify most of the oil, the soil samples, silty clay samples, the clay silts, and then some of the gravelly sands samples, and then have been able to estimate the concentrations using the exact number that is given by the TPH index. And so it shows that the TPH index is a better predictor for oil concentration than what we use in most of the models, which is the 1725 nanometers. So further, we try to use an in situ measurement, where we just got a box of sand and then poured oil into it, and to see how we can predict or we can measure this oil at depth. So we use sort of a penetrometer kind of probe. You know, this is what you have at the top picture there. And then we use a 3 profile and then measured. So we use a 3 profile line and measured the oil, you know, at depth. So from 25 millimeters, 50 millimeters, 75 millimeters, and 100 millimeters. And then we use the TPH index to see if we can actually get the exact concentration of this oil, you know, within the box. And this is what you can see from the outline there. We're able to use the slice marks and able to get the different concentrations of the oil at depth. And we tested it at a dry condition, which represents sort of an arid condition. And then, of course, in wet condition, we're able to also get that. So in technical applications, it is possible that this particular index can be taken to the field. You can get a spectrometer, go to the field, get some background, some sort of information, you know, on the soil, the type of soil you're going to use. And then you can develop a sort of a calibration where you can compare the concentration with. And then it can definitely serve as an alternative to low background oil detection. And because we have tested in different, up to 26 different soil types, both artificial and natural within the country, this particular index is applicable in different soil types. So in conclusion, the visible near-infrared spectroscopy can offer an option for low background oil concentration, and it is possible to meet most of the requirements of the 100 milligrams per kilogram. It is applicable in different soil types, like I have said. And for those who are interested in oil prospecting, and because it's able to actually show very low concentration, you can use it the other way around. You don't want the contaminant, you can do the prospecting. Okay. And so finally, I think the method that has been developed is both rapid. It does not need sample preparation, just like GC and other things. It is rapid. You can take it to the field and just stick your probe, and you're able to get a lot of information about it, and it can be used effectively in oil spill response protocols, especially in the soil. Thank you for this.
Thank you, Hamlet. Yeah, I just think it's a great bit of research that can be used in all sorts of different applications. So, yeah, any questions for Henry?
That was really good. Thanks very much. When we were sampling fuels for contamination, we used a near-infrared spectrometry all the time,
yeah.
And we were able to identify difference through the curves. We were able to measure what contamination existed and even what different type. So it is very possible, and some of these near-infrared technologies have been actually sort of reduced down in size to being virtually instant readouts.
Yeah.
Have you gone to industry to use micro sort of mass spectrometer or infrared spectrometry equipment at all?
I haven't gone to the.
There's a company up in Oxford who sort of seems to be has floated somewhere and maybe owners a lot of money, who actually developed some of this stuff. So it does exist outside of the academic world as well.
Yes, one of the things I have had a conversation with my supervisors. For example, most of the spectrometers measure a broad, band from 350 to 2,500. And what is the way forward? We can actually isolate some of these narrow bands just to build a simple spectrometer and maybe to put it on a robot or an unmanned aerial vehicle or something, and just take it and just use the exact bands instead of using the entire spectrometer. Yeah.
Okay, I mean, I'll be fair, I will talk afterwards.
Okay.
Brilliant. Thanks, Mark. Anybody else? No. I suppose I've got a question is what next for the technology, and obviously what next for you? I know you're looking for gainful employment, but yeah, what next for the this technology, do you think? How do you think we can take it from your research to a practical tool?
Yes, at the moment, just like he mentioned earlier, it is possible to have a minute portable device that can be taken into the field.
Okay.
And then isolate these particular signatures that are identified, and then to be able to build fit for purpose, instead of just using the broader band of the entire thing to the field. Yes, so that is the next thing I believe will be quite useful. And possibly because the index that I developed is physics-based, other stuff are, based on statistical base, but this is part of physics-based because I consider the combination bands and then the overtones and stuff, it is possible to also try this in the, the marine environment. I haven't done it. I haven't conducted the experiment. So it could be another step forward because it's able to detect and find out the oil signatures, and it may be able to quantify better than the existing techniques.
Okay, good, thank you. Yeah, so I think that was an answer. That would be great. Anybody else? Okay. Thanks, Emily. Best of luck in your job. So take us up to lunch now.